In this video, we will talk about what complete graphs are. All right, so I want to start with the definition, which says that a complete graph on n vertices is a simple graph. Remember that simple meant there's no multiple edges and no loops. Simple graph where every pair of vertices is connected with an edge. And I denote a complete graph as capital K subscript n. So n represents the number of vertices. Okay, so let's do an example. Let's draw some of these complete graphs. So K1 is a complete graph with one vertex. So let's draw one vertex. I can't have any edges here because an edge would only be able to connect it to itself, but then it's not simple because it would have a loop. So it's just a vertex by itself, which can happen. A graph can have a vertex just by itself. K2 would have two vertices, and then any pair of vertices has to be connected with an edge. So, okay, we draw one edge connecting them, and that's K2. K3 has three vertices, and then I connect each pair with an edge. So connect those two, and then connect that remaining pair, and that's K3. K4 has four vertices, and then I connect all of them with edges. So let's connect this one to the other three. Let's connect this one now to the others. Now there's one pair left to connect, and we got it. That's K4. Remember that when two edges cross like this, that does not mean that there's another vertex there. There's only a vertex there if it's drawn in. So it's totally fine for two edges like that to cross each other and not actually have a vertex there. K5 has five vertices. So let me draw 5, and then I connect each pair. So let's connect this one to all the others, connect this one to all the others. I'll connect this one to all the others. And now there's one pair left to connect, and we got K5. Okay, so what's true about the degree of the vertex in a complete graph? So if I focus on K4 and I pick any one of the vertices, well, there's one edge, two edge. It shows up as the endpoint of an edge 3 times. So that happens to be the number of vertices minus 1. So the degree in general is n minus 1. Okay. All right, so I want to end this video with our first theorem about graphs. This is called the Handshaking Theorem. And I'll show why it's called that, where this term comes from. So I'm going to let G be a graph. So remember, this is my notation for graphs. V is the set of vertices, E is the set of edges, and let's say that there are n edges in this graph. So we saw sigma notation back in, section 2.4? Remember, that just means we are summing up something, adding things together. So here we are adding up degrees. We were adding up, so V, lowercase v, represents one vertex. Capital V is the set of all vertices. So what this is saying is we'll sum up the degrees of all the vertices. This is the sum of the degrees, of all the vertices. And what the theorem is claiming is, well, that should be equal to 2n. If we sum up the degrees of all the vertices, it should end up equaling 2n. So let me draw some examples to get a conceptual sense of, well, why do we expect this to be true? So I'm going to draw a couple graphs. So let's say in this first graph, I have these 3 vertices. Let's say that these two are connected, but then one is by itself. So I'm going to keep track of what the degree is for each of these vertices. So the degree for each one. And then I'm also going to copy this over and draw it one more time on the side, but then I'm going to modify it. And so I'm just separating out these two graphs. And in the modified version, what I'm going to do is I'm going to add an extra edge connecting those two. So now for each of these graphs, let me keep track of, well, what is the sum of the degrees of all the vertices? And then let's also keep track of the number of edges. I want to keep track of both of those things. Okay, so I'll make a little table. So for this first graph here, if I write down all their degrees, well, this vertex is a degree of 1. There's one edge that shows up as an endpoint that has this vertex as an endpoint. This vertex, its degree is also 1. But that third one, well, there's no edge connecting to it, so its degree is 0. When I drew in this extra edge, what that does is it adds 1 to the degree of this vertex, and it adds 1 to the degree of that vertex. So let me give myself a little bit more room here, because this is a bit cramped. Okay, so the degree of this one is 1. That one up top is now 2. And then the one over here, there were no more edges drawn connecting to that, so that just stays as 1. Okay, so if I add up the degrees in these two graphs, in this first one, I'll get 1 plus 1 plus 0, which is 2. And then it just had 1 edge. Okay, if I do it in the second graph and I add up the degrees, I'll get 1 plus 2 plus 1, which is 4. And this one had 2 edges. But notice that, well, for each of these, I double the number of edges to get the sum of all the degrees. And that's exactly what the theorem says should happen. I should multiply the number of edges by 2 to get the sum of all the degrees. Okay. All right. So the key idea here is that anytime I draw an extra edge, like I did here, it adds 2 to the total degree count. Okay, so before my degree count used to be 2. When I drew in that extra edge, well, it added 2 more to the overall degree, to the total degree. So we are ready to write that up now. So each edge contributes 2 to the sum of the degrees of the vertices. The degrees of the vertices. So anytime I draw an edge, it adds 2 to the sum of the degrees of the vertices. And then all I need to know then is, well, how many total edges are there? So I'm given that they're n. So since my graph G has n edges, well then the sum of all the degrees, this is my notation for the sum of all the degrees, well, that's just going to be equal to, you take the number of edges, n, and you multiply it by 2. Because each time you draw an edge, it adds 2 to the number of, it adds 2 to the total degree count. But that's exactly what we wanted to show. And that completes the proof. So I mentioned at the beginning that I would talk about, well, why is this thing called the handshaking theorem? It doesn't seem like there's any handshakes here. But I could actually think of each vertex here as a person. Think of each vertex as a person. And anytime there's an edge drawn, think of that as a handshake. So in this first graph, these two vertices, these two people, they are shaking hands. But no one's shaking hands with this third person. And in this second graph, well, one handshake happens between these two people. One handshake happens between those two people. So in this context, what the sum of the degrees is doing is it's counting, well, how many times did each person shake hands? So this person shook hands 1 time. That person shook hands 2 times. This person shook hands 1 time. So the total number of times people shook hands all added together was 4. And each edge represents a handshake. But anytime I have a handshake, there are 2 people associated with it. That's why I have to take the number of handshakes, which is n, and multiply it by 2 to get this total count of all the degrees added together. That's conceptually what's going on, thinking about this as terms of handshakes and people shaking hands with one another.